Rumor has it that they built the engine to support 850 horsepower. It's not a good enough excuse for me saying, sorry, the engine broke. I was supplied a part that wasn't built correctly.
Right.
But if you had a block that came back from the machine shop that had a thou of taper, would you take it back and say, you guys messed up?
Yeah, I'd be like, hey. Absolutely.
Yeah, we run it and it runs great. The reality is like nothing's perfect. And especially when you put it into a dynamic situation, it's even less perfect.
So not to burst anybody's bubble, but this is nothing new.
We're just going drifting. We're so below the capability of all of this stuff.
Hey, if you like what you're watching, do me a favor. Go check out the Hagerty Drivers Club. 24/7 roadside assistance with flatbed towing, subscription to our award-winning magazine, and more. Sign up today. Links right down here in the description. Hey, this is Davin with Redline Rebuild, and today we are off to California to meet up with Stephan Papadakis of Papadakis Racing. Now, if you're scratching your head going, who the heck is that? You've been under a rock if you're into drag racing, because he is the man when it comes to sport compacts. In the 90s, he set 200-mile-an-hour record. Then in 2004, he moved on to drift cars and built some spectacular drift cars, and of course, has been very good at those as well. So we're gonna head off to his shop now and see what it takes to build a Formula Drift engine.
So what are we gonna do here today? We have this beautiful aluminum block and they're all in a row. Now what?
Yeah, so this is our 3-liter inline 6-cylinder engine out of a GR Supra. And we're building this engine for Ryan Turek. We're actually putting one of these engines in a GR Corolla and it's rear-wheel drive. So it's a big modification for a little GR Corolla,
for sure.
But it's gonna have a 1,200 horsepower 6-cylinder engine. Okay. So the first step, now that the parts are all machined and all laid out and clean, is we're gonna measure all of the bearing clearances. So that's the oil clearance in between where the rod and the main bearings go and the crankshaft pins.
You check it typically in 2 spots then?
Yeah, just to make sure there's nothing really weird.
Mm-hmm. I mean, being ground, there shouldn't be any kind of egg shape, but
yeah,
it's
just these
possible.
weird things that it's just,
right.
You just kind of, it only takes another moment and I just know. It's not a good enough excuse for me saying, sorry, the engine broke. I was supplied a part that wasn't built correctly. Right. I need to know that part was built properly and sized properly before I put it in the engine, because I'm the builder and it's my responsibility. So this is an OEM crank, but it's been straightened. It's been detailed a little bit with all the oil holes and then polished.
Do you bring in a crate motor type setup, meaning it's already assembled and you tear it down?
It's an engine.
Manufacturer?
Yeah, so the engines are only available in completed long block form.
Right. Okay.
And so we get a new one in a box.
Yep.
It's a part number for a GR Supra. And we disassemble the whole thing and then do all of our mods and machining and then put it together. So this is a crankshaft that was an assembled engine, but it's never been run.
Right. Okay.
It's all done. That's all measured.
Okay. Now you have stock specs that you have at least to
I've got
kind
my
of compare
old,
them to. Right?
Yeah, this is one of a previous engine that I did and some of the clearances.
Yeah.
And so what I like to do is just sort of look back and see
if something's crazy.
Yeah, you know, get an idea of what sometimes, because these engines they're kind of doing production changes sometimes, and I'm making sure that the parts we're getting are matching what I'm expecting.
Yeah.
All right, so now with this dial at 0, the outside to outside of this is exactly the same as the diameter of the crank pin. So now that that's all set, I'll actually check it again a little bit. I'll then put up the bearings in here and then start checking it. And the difference is the oil clearance. Yeah. This has billet caps on it, billet steel caps that we've added ring dowels to it instead of the factory teeth where it bites in to center the cap. And it's been line bored, or they have to, the caps come undersized, so they have to then match that and then line honed after.
Yeah. So here's what he's referring to as the stock cap is this casting opposed to the steel cap, which the steel is going to be stronger. And of course, adding the dowels, as we'll see here in a second, helps align it or keep its alignment
the cast caps, they can be too brittle and crack.
Right.
They haven't necessarily happened on this engine, but engines we've run in the past.
Yeah.
Once you get to really high level,
Yep.
you can crack the cap. So these are stronger.
Yep. Yep.
Initially, we had them built to replicate the factory stuff.
Right.
And eventually, we decided to put ring dowels in it. But we had the main caps already machined
Right.
with those teeth. So now we just, shave them off
Yeah, because it doesn't. Yeah.
or shave them flush.
Yep.
The bottom bearing has the oil hole,
Okay. Yep.
or the block side one,
Yep. And a groove.
and the top one is plain.
Yep.
And then the tangs are in different places,
Right.
so you actually can't swap them.
Yeah. So what's your torque sequence and then torque spec at the end of the day?
So 60 foot-pounds,
Okay.
and I'll go in steps from 20, then 40, then 60.
Yeah.
Money.
Well, I guess what's the clearance that you prefer? I mean, do you do a
1.820.
Yeah, thou.
Two
a thou
thou, two thou, give or take, a couple thou.
per- Yeah.
You can run these tighter, you can run them looser.
Right.
But aluminum block, we tend to get the blocks pretty hot. And so that'll happen is your oil clearance will increase. So you don't want to start with too much oil clearance cold, because once everything gets really hot, you're going to put too much clearance. Your volume needs to be, you may not have enough volume in the pump and your pressure drops. Then you can start running into issues.
Right. Yep. Yeah. You starve it. Okay.
So this bearing's a little tighter than I want. So I'm going to actually change half of the bearing to a slightly thinner bearing. You can actually match bearings. So they make a standard kit and they make a 1/1000th extra clearance kit, but you can take half of the bearing from the extra clearance and mix it with the standard and get half a thou more clearance.
Now, do you have a preference on which side you put that?
I used to, but I don't think it matters.
Yeah.
So this is an extra clearance bearing. Okay, so at first it was standard bearing, and now it's extra clearance standard. Call it 2-1. It's fine. Yeah, 2-1. So we're good there. So I've got the crankshaft diameter on the journal. I've got the bearing that was installed and the measured oil clearance. Main number 3 has a half that's standard and half that's extra clearance. And number 7 has a half that's standard and half that's extra clearance.
Right.
And I've also written down the torque and the fastener. Normally I have the part number here, but I'll have to fill that in later. And then we're all good there. And the next I'm going to move on to the crankshaft end play.
All right. So we're setting this in dry. So,
I want it to float
yeah.
so I can do my proper measurement.
Okay.
And when I pull it back out, I don't want all the bearings to stick to the journals and
Okay.
fall all over the place.
All right. What is your in-play
So I'm looking for
requirement?
2 to 8 thousandths. We got a huge range.
Yeah.
We just want something,
Yep.
just not too much. And because the block is aluminum, I'm actually going to put the dial indicator on the crank.
Yeah.
It's like 4. Okay. So we're fine. Yep, so I've got 4 thousandths of end play. I'm not going to turn the crank or do anything because it's all dry and everything. But I just want to make sure that we've got some thrust.
Yep.
And
you can see too on every one of your main caps you have all kinds of clearance because thrust is only controlled here, or in play is only controlled here, but you don't have any crash like we were talking about. So you can visually see that there be no other issues with any of the other caps.
Right.
Is what I'm getting at.
Yeah, we have some billet cranks that we run. And see how the radius is undercut?
Yep.
It's not on our billet one. So then on some of the bearings, we have to clearance them for that.
Yes. So in theory, your thrust bearing controls all your in play. But if you were to have an issue, you'd be able to visibly see it because you're only talking about 4 thousandths clearance. So you have a ton of gap between this saddle and the crankshaft, and as you go down every one of them. So that's why he's not putting on any of the rest of the caps.
Yeah, so any adjustment would happen here.
Right.
Any problem could happen out here. So what's going to happen is I've now checked the thing that I can possibly adjust. And then when we do the final installation, everything's torqued down. I'm then going to check the thrust again and make sure it's what we expect. What I'm going to do now, I'm going to put all the oil squirters in and then lube this up and put the crankshaft in and torque it in. And the crankshaft will be installed. So the way this works is it goes from the oil galley. Yep. It's got an O-ring. It's got a little check valve. So it has to have a certain amount of pressure before these open.
Yep.
And the reason they do that is so when you start the engine, you're not leaking oil out of here until the oil pump and everything starts getting pressure. Then it opens those.
Right. And the whole point of those is to cool the bottom of the piston, right? And lubricate the pin.
Yep.
So not to burst anybody's bubble, but this is nothing new in the world of engines, because we were talking earlier, that 50 stove bolt had squirters in it.
I think a lot of this stuff was in airplane engines in World War II, right?
Absolutely. Yep.
They had direct injection back then. They
Yep.
had all kinds of cool stuff.
Yep.
Zero-ish. 7-ish.
So we're good. All right, so we're at the spot now. You're going to go through and you're going to torque all the caps down with the bearings in and measure the oil clearance similar to the crankshaft. But you're going to use a rod stretch bolt, or a rod stretch gauge. Help me out on how you're going to determine what torque to run those rods to.
So this ARP bolt that comes with the SuperTech rod is a 3/8 diameter, and the 625 plus material that they use, they recommend about 6.5 thousandths of stretch. So what I'm going to do is do like a pre-torque to get everything seated a little bit. Then I'm going to back it off, check the bolt length with 0 torque on it, and then I'm going to bring it up to like a low torque, like the low end of their range, 50 foot-pounds. Then I'm going to check the stretch. Then I'm going to start creeping up higher on the torque until I get to the stretch that I want. I'm going to then note that torque. And then later on the next rod bolt, I'll be able to go to a torque just under the one that I got the proper stretch to, check the stretch, and then potentially creep on it up on a little bit more to get to the stretch that I want. If it takes a bunch of torque to get to the stretch that I want, I think there's a problem. So it allows me to have multiple data points, not just one.
Right, okay. Yeah, because I was curious as how you're going to get to one finite torque spec across all the rods. But you're telling me, what I'm hearing is you're not really all that concerned about that.
The torque can change depending on the lube and how I lubed it potentially. It could be, there's all this extra friction. Yeah. But the bolt sees friction, that's part of it, but really it's how much this thing is stretching.
Right.
That's really the clamping load.
Correct.
And so I'm just really worried about the clamping load. The torque is just another data point,
reference, yeah.
Just a reference to make sure that if the torque is way off to get to my stretch, potentially there's an issue. In the past, I would never look at the stretch and just torque it to the recommendation and never had a problem.
Right.
So it's rare that if you get somewhere within the spec that you're going to have a problem. You're probably going to be fine because typically when you go to an aftermarket rod and a high-end rod bolt like this, you're so below the capability of that part that even if you're off a bit, as long as you got your bearing right, you're going to be in a good spot.
Yeah.
It's when you start getting to the limit of everything, that's where you need to work on more precision, and we're getting closer to that with these, as we make 1,200 horsepower.
Correct. Right. Okay. Yeah.
If we were building an Indy 500 motor and this thing's going to get sent out to win the championship on that, and we had a whole crew of people and doing all this logging, absolutely, I think you should probably serialize every number, and how many cycles this bolt has had, and you go through that whole process. We're just going drifting. So we're so below the capability of all of this stuff. And so we can run a heavier bolt than we need that takes more load. We can run a bigger rod than we need that takes more power. if we're really optimizing it, all the stuff would be lighter weight. All the stuff would be optimized, and we'd be so closer to the threshold of what is available.
Yeah, you don't need to be at that hairy edge.
Nah. I found that I can get to the stretch that I want with less torque, less friction with the CP Corolla lube than the ARP lube.
That's interesting.
So I actually use their lube instead of the ARP stuff.
Gotcha.
20, and then I'm going to loosen this back to 0, so it's loose. I'm going to check the bolt length. 0 this. I'll do like 25, and then 50. Our stretch is 4.5. So that's 6.5, and it took 75 foot-pounds.
Gotcha. So 20 over their recommended. Well,
I've almost always found that to be the case.
Their reference point.
Yeah, I've almost found that always to be the case. Like they'll have a maximum that they want you to torque it to, and it usually takes way more to get it to the stretch.
Sure. All right, so what did we end up with? You obviously we went through the whole process, got everything torqued down. It looks exactly like the same when we started, but you know.
So I started with the standard thickness bearings, and the clearance was about 0.5 thousandths more than I wanted. So I got my set of oversized bearings that are a little bit thicker, and I used just the the bottom half.
Yep.
And so I was able to get that 0.5 thou less oil clearance, and they all came out within 1/10, so which means that the rods are consistent, the bearings are consistent, and we're ready to go to the next step.
Excellent. And again, to kind of reiterate it, you're focused on torque means nothing, quite frankly, right? You're only worried about clamp load, and bolt stretch is a better indicator of clamp load than torque is.
Yeah, if the torque it takes is between 70 and 80 foot-pounds to get to the stretch that I want, and if I have an outlier where all of a sudden one of them only takes 50 foot-pounds to get to the stretch I want, there's probably something wrong. Right. I should look at it. Could be the bolt, could be something else, or if it takes 100, which is very unlikely, but it could be I didn't lube that bolt properly. There's much more friction. So I wouldn't say it means nothing, but I'm trying to keep it within that range.
Okay.
Yeah.
Gotcha. All right. Excellent. Where are we going from here?
So next, we'll bring the block back into play here, and I'm going to measure the bore, measure the pistons, make sure we have the right piston to wall clearance, which has been checked by the machine shop, but I'm going to check it here and put it in my blueprints.
So at this point, all you're really doing is making sure you don't have a bore that's too tight.
Yep. But what's interesting is this is within a couple of tenths from the factory. So the theory is that they're doing this on purpose, because every block we've had has the same taper and is all within a couple of tenths of that taper. Yeah, so the theory is, like, imagine, and this is just the theory, but imagine you bolted a deck plate on, you bolted a head on, and you bore and hone this thing perfectly straight with the torque and everything, exactly how you want. And then you unbolt the head, and it's going to distort in some way. And then you're able to digitize that distorted bore. And now with CNC honing techniques, you're able to get in there and final hone it distorted.
Right.
And then when you bolt the head on, it's round. I don't know if that's true,
maybe,
but like that was we'd hope that like technology was at that level.
Sure.
But I bet the situation is that it may or may not have 1 thou of taper, and it probably makes no difference on the dyno and longevity. Or maybe they start with some sort of taper, and after 50,000 miles, it's straight.
That could be.
I don't know. But if you had a block that came back from the machine shop that had 1 thou of taper, would you take it back and say, you guys messed up?
Yeah, I'd be like, hey. Absolutely.
Yeah, we run it and it runs great.
Well, I'll tell you what, though, to go back, that kind of throws some things away with you got to run a torque plate on the top of these.
So I've had a conversation with about that. Right. I'm like, well, yeah, but you're putting a torque plate on it, and you're boring it, and you're honing and all this stuff at room temperature. Right. The thing doesn't run at room temperature. Shouldn't you run it hot? And I guess for a moment, the machine shops were running like hot oil or something through it to do it all at that temperature. Right. And then the conversation quickly goes into, well, you can't get together all those parameters and get it perfect. So what are we making it perfect for? And so I'm a firm believer in have a tolerance and make sure you're within that tolerance. And at the end of the day, what we're trying to do is win races. We're trying to win events. And so we need to spend our time, our finite amount of time on things that have tangible results there. So the things that we can do today that will give us tangible results is reliability, consistency, making the power that we want. And if you're telling me that somehow this bore being all perfectly cylindrical versus a thou of taper will lead to more of those tangible results, I'll do it.
Right.
But at no point have I ever seen a situation where this engine had a problem because it had a thou of taper.
Understand? Yeah.
It's the machine shop. Like when you have a customer that's paying a bunch of money, they want it to be perfect.
Right.
But for us, the reality is like nothing's perfect. And especially when you put it into a dynamic situation, it's even less perfect. So understand your tolerances and work within them.
Right.
Yeah. But a lot of people don't like to hear that.
No.
No.
Not a lot. Pistons are all assembled. Now, the only thing I noticed that you didn't do that I always do is I use a ring spreader to open up the rings to set them on, and you sprung it on. Now, is that because I'm using a thicker ring and you're using a thinner ring? I'm guessing, but
It could be. I have a technique where the second ring, the cast ring, I'll hold both ends on one side, and then I'll actually spread that one and bring it over.
right. Okay.
I don't spiral that one because it's more brittle.
Yep.
The top one, I will spiral on because I don't want to flex the top one as much because it's steel. So I use a different technique on either one.
Okay.
I don't know. I've used a spreader, and I feel like they spread them more than they need to get on there. So I just hesitate.
What's your magic in positioning the gaps?
Oh, sure. So what I do is I put the ring. Sorry, I position the oil ring spring with the gap at 6 o'clock,
Okay.
and then I put each one of the gaps at, call it what is that, like
The rails.
the rails like
45.
4.5 like 4:30 and maybe like like 7:30.
Yep.
And then I do the second ring opposite of that on this end.
Okay.
And then I do the top ring over here. I got this one because an old Honda service manual that I used to do from the Civic Motors and stuff. That's how they aligned it all. And I've just done it like that ever since. And what ends up happening is this stuff moves around in service anyway.
Exactly.
So I just place it somewhere logically, and then it kind of moves wherever it does, over the life of the engine.
Right. So discussion-wise, there's always 16 different opinions on which ways it should be. My thought is just put them all the same. Not in line, because you wouldn't build a house with a brick line straight up and down. But you stagger everything. But as long as you stagger them all equal, or between the pistons, meaning they're all in the same position, then I figure that's the best.
Yeah,
way.
I have a system.
But that's
I'm
exactly,
consistent
That's
with
the
it.
same way I do it too. So
Yeah.
just curious.
Oh wow, what a coincidence! Yeah.
Yeah.
And I'll put a nice coat of assembly lube on the rings, the skirts, the bores, and also the inside of the installation tool.
Correct. Yep.
And then we'll get them in, make sure everything feels right, and then torque them up with the rod bolt stretch gauge like I was doing. I'm going to do the exact same process tightening the rod bolts as I did when I tightened the rod bolts when I checked the oil bearing clearance.
Okay. Makes sense.
Yeah, just it's all about consistency. Yeah.
All right. And assembly lube versus engine oil.
I'm not sure. I would go with the rings manufacturer's recommendation.
Right.
In this case, there really isn't one. So I've had good luck with this stuff from Total Seal. It's just a assembly lube. It's a little bit thinner. It's blue, which is kind of cool. And these guys do rings.
Yeah.
That's their main focus is rings. So there's some trust in that.
Absolutely. Okay.
Yeah.
All right.
But I've assembled them with WD-40 engine oil, and I don't know if there's that much of a difference.
Yeah.
But someone, I'm not the ring expert. You know, that's just the way I do it.
Okay. Cool. Here's the question that we've had multiple times as far as given break-in procedures, right? And engine oils, but you still have rings to seat. And then the dilemma of, does a ring seat with synthetic oil or not? What's been your
I think if the
experience?
Yep, my experience is if the block is bored round and the hone is done properly, that matches the rings, it doesn't matter what you do. This assembling is just going to work. I'm not convinced that there's a particular break-in scenario unless something's incorrect and then needs to break in.
Okay.
Round cylinder, I mean, all these factory cars all on the street that don't burn oil and are perfect, they put synthetic oil in it right away. There's no high zinc anything in those things.
Right.
I think a lot of it's marketing.
Fair. I wonder if they have if there's any specific oil for their first fill though from the factory, meaning, you know, those companies are large enough to have a specific mixture for their purposes.
I bet you.
Do you know what I mean?
Yeah, they're probably designed to go as long as the warranty.
Well, 100%.
That's my theory. It can't be, that initial break-in oil can't do anything that would mess up emissions. So it's not going to be like a special high zinc. It's not going to be any like
I didn't think about
weird stuff like that.
That's a good point.
Yeah.
That's a good
It
point.
has to be the cleanest stuff.
Right. So we have our pistons in, everything's torqued down, double checked, make sure the oil squirters are squirting in the right direction. And now we're gonna move on and put the girdle on and the oil vacuum pump, you said. So that's interesting. That's different. And it's chain driven. And the other thing we talked about earlier is the sprocket that's on here. Instead of being slipped onto the end of a snout or whatever, it's actually machined onto the crankshaft, which is a pretty interesting process based on, well, how it has to be there. And the timing chain is on the back end of the motor instead of the front side, traditionally. Okay. Cool.
Yeah, there's some advantages to that. So the timing chain and all this gear on the backside of the engine, though it may be more difficult to service, hopefully you don't have to do that, it actually can add some more stability to the whole cam train. So typically on one of these engines, or almost all engines, there's harmonics and twisting going on the crankshaft. Well, those harmonics then transfer into the chain that's on the front of the crank, traditionally, and that goes up through the chain and into the timing gears and everything, and through into the cam train. So having the mass of the flywheel and the timing chain and everything here on the back can actually make have less harmonics in a more stable cam train. So normally this takes a torque to yield bolt, and I've replaced it with non-torque to yield stuff.
And obviously there's no timing, it doesn't care.
Yeah, there isn't. There's like some color and stuff on it here, but it doesn't seem to matter.
Tell me there's a tensioner on that.
Nope.
No?
So it just cruises along with reverse thread bolt.
Yep.
That's it.
It looks loose. That's right. Yep, that's what I was talking about. Holy sloppy. I guess. I mean, there's very little load on it, right? All right, so now that we have the oil system on and, of course, the short block, were there any changes that you found you had to make relative to oil system? That's fairly common.
The oil pump is quite good. It has a variable displacement, but and it's controlled by the ECU. What we found is we actually just don't even, we let it self-control and we just run it at 90 PSI all the time. We've tried to control it, but it ends up having some short block issues where we have some bearing failures. So I'm not exactly sure if it's the control strategy or just for the power that we're running, we need to run more oil pressure. But we just run it
wide open all the time.
Yeah, run it wide open all the time.
All right, cool. So then from here, we're moving on to the timing chain.
Yeah, so I'll put the timing chain on, the guides, and the timing cover. And I do all that all upside down so the chain can sort of hang out the top of the engine.
Right.
And then once I'm done with that, we'll flip it over and start putting the cylinder head on.
Okay. Cool. Now we get to see his sealer of choice. Surprised they don't have like a gummy seal for that.
Most of the imports, almost every import engine that I've worked with now is just
right down to the
silicone.
Yep.
A special service tool.
I got the same one. Looks like the gray moto sealant.
Import gray. It's not the tackiest, it's not the most robust, but it when you work on these things a lot, we can actually clean it off relatively easy.
Right.
And kind of do it again. These new style seals don't have a spring and they're very low tension. And I've tried to install these without the special service tool, but this is a precision machined tool. So the seal goes over this cone and just perfectly installs onto the crankshaft flange.
Yeah, that way you don't roll the lip seal in.
Yeah, we modified the pan. This engine doesn't belong in the front of a Corolla, so we modify the oil pan a bit. And where we go into the pan, it actually would hit the oil pickup. So we've just removed some material from the oil pickup.
So it must be like a cross member or something that has to be in front of underneath the pan at that point.
It's the rack.
Rack
pinion.
Okay.
Yeah. The pan sort of has this little angle here, but we had to notch this area.
Dish it out.
Add some material back in, some aluminum, and then weld it back up.
All right, so pulled out a couple of valves and springs for us so we can see this. These things are very small from what we're used to using. And extremely light. I love the beehive spring. Of course, you said a titanium retainer. And these specs down here are the keepers. What are the size on these valves? They look like, what, 25 millimeters, roughly?
Yeah, so this
like
is a 5 millimeter stem and then a 6 millimeter stem. And the size of the valve, That's a good question. I don't remember off the top of my head.
Right.
But the intake is a 30 millimeter.
30.
And then the exhaust is 28 and a half.
Okay. Of course, times 2. So that's where you're getting all, getting the flow from that standpoint. Now, are they any kind of special material? These obviously have a coating on the backside.
Yeah, so this is a coated steel valve on the intake, and everything is designed to be as lightweight as possible. And that way you can get away with way less, spring, right?
Right.
And then the exhaust is Inconel, and it's sodium filled.
So the head is already assembled because the guy that does your port work, of course, brings them to you assembled. Where is he gaining the main, what's he doing from the stock standpoint? I mean, obviously they flow pretty well to begin with, but there's always room for adjustment here or there.
Yeah, if you want, we can pop the head down, and then I'll show you on the head. So the main area that we gain flow is the transition from the valve seat to the pocket area in the port here. The factory one, they don't spend a lot of time machining it. It works well for their application. But once we smooth that and really help the flow, where it transitions from the port to the valve seat and out the valve, there's a lot of increase there. We also open up the exhaust port a little bit, and then do some deshrouding and a little bit of work in the chamber.
Oh, okay. Very nice.
And it being turbocharged, and for us using a very broad power band, we wanted the engine to spool up relatively quick. So maximum power and maximum flow is not what we're aiming toward on this. It's really a really broad power band, and you can get into trouble if you make those ports too large and you get the velocity down,
right?
And then at lower RPM, it can actually hurt it quite a bit. Another interesting thing here is you'll see these plugs. So this is where the direct injection used to go in for the fuel, and we put plugs in there and then only use port injection. So the fuel only comes in traditionally, through the intake port before the intake valve.
Right.
And
so what's the reason for that? Because in general terms, direct injection is the best way to fuel.
For the E85 fuel we use and the amount of fuel we need to make 1,200 horsepower, they really don't have good pumps and injectors and stuff like that we could use for this. So we think it's more competitive for the car and more reliable to just have a simple 6-injector port injection setup.
If you were to keep the direct injectors, is there a limitation on how much pressure they can open against?
The fuel pressure is 2,000 plus. So it's much higher than what we're used to in port injection. And that's one of the reasons why you see mechanical fuel pumps making a comeback that are cam driven, because those are the pumps that can supply such high pressures into the chamber.
Right. Okay. All right. Well, let's put this back up in the stand so you can throw those 2 valves back in, and you can show me your fancy tool there to put that in there. Okay, so we're on to putting the cylinder head on, and you have a solid copper gasket, which is fairly traditional, but these rings are not. So explain those to me. What's going on here?
Yeah, so the copper head gasket only seals the oil and water ports. All the combustion is actually sealed with this copper alloy, call it fire ring. Okay. And it has a unique profile to it that sits in a groove on the top of the block, and that locates it.
Okay.
And it actually sits 3/1000ths proud of that copper gasket. So when you clamp the head on, it really puts most of the pressure on that sealing ring, so you really have a good seal in this area. And because it's slightly proud, we have to put a lot of silicone on the rest of the copper gasket to make sure that we don't have any water or oil leaks over time.
So do you get a little bit of a crush? I would assume you get some crush.
Yeah, there's a magic with the alloy that this copper is made out of.
Right.
So it's strong enough, but at the same time, you have to balance that with the amount that you're torquing the head down, so you don't deform the head too much in those areas. Yeah. So it's a balance between getting everything clamped and having this isolated torque area or clamping load area, but not distorting and messing up your head.
Right.
Well, a lot of this stuff I learned sort of by doing. I didn't start in a shop with a mentor. So I've just sort of made most of the mistakes and got experience the hard way versus someone like telling me the easy way first.
Yeah.
Because when I started, it was pre-YouTube.
Sure.
So my guru, or the thing I was learning all this stuff from, was the service manuals. I really like to read instructions. So I'd just read all the service manuals and go through all the steps. And service manuals were, I think, better back in the 90s. But yeah, that's where I learned to work on a lot of stuff. And friends too. But we're all pretty much, backyard garage mechanics. And so we didn't necessarily have best practices. It wasn't until much later that I got, in groups and friends that were more meticulous than I was, that I could learn some better best practices. We're doing it. All right, so these are the knurled ones we're talking about.
Right. Okay.
Yeah, so knurled side goes down, dry. Yeah, we want the nut to only spin on the washer, and we don't want the washer to spin on the aluminum cylinder head. So they texture the bottom side of the washer so it doesn't want to spin. This is where the cylinder head bolts to the timing cover. So there's 5 bolts there that need to be torqued. Head is now torqued. And yeah, that's it. Head's on.
Easy enough process?
Yeah, it's the silicone that makes it kind of a pain, but blowing head gasket's worse.
And obviously the factory gasket isn't sufficient to hold the amount of boost.
I think that they might be, but we ran these on the 4-cylinder engines where we're making, 250 horsepower per cylinder.
Right.
And when we started developing this one, instead of finding out the limit of the factory head gasket, we just went to the one that we knew had a really high limit.
Yeah. No, that makes sense. What do they rate them at? Is there a rating for them?
Rumor has it that they built the engine to support 850 horsepower, but that's urban legend, and I've got no actual
Gotcha.
Quotes from anybody. Yeah. But that was sort of the theory is when they designed this engine, they did want a really high margin.
Right.
Yeah.
Right. Yeah, margin error.
Yeah.
Now, how about with on the fire rings? Do they have you can stock is here, but adding the fire rings, you can bring boost up to this number.
Yeah, so really, when you really get down on the head gasket sealing, it's not really the power that'll get to, it's how much detonation or pre-ignition or something goes wrong, how forgiving it is at that point. You have your normal high cylinder pressure as you're making this high horsepower, but you've got these gnarly spikes when you start having detonation,
right?
Pre-ignition.
When time.
Yeah, so it's just being able to deal with those spikes more. Okay. It makes the engine more forgiving, and then if you have a small problem, it doesn't turn into a large one.
Right. Okay. Interesting. Well, I guess I'm going to say this. There's a lot of parts in this, as you know, but what are we all looking at? I mean, there's rocker stand, there's caps, there's, your rockers, and for all intents and purposes, a hydraulic lifter. Not really, though, right? Is it just kind of holds there and takes up slack, I'm assuming?
It's a hydraulic lifter.
It is?
Yeah.
Okay.
Yeah, it is.
All
Yeah.
Show me how this works. Or explain some of the parts here.
Yep, so we'll put in the normal intake and exhaust cam. They just have a single lobe for each valve. This is what we'd call maybe the third cam. And the intermediate rocker, these over here, ride on that. And depending on the location of that third camshaft, it changes the amount of valve lift for the intake cam.
Okay.
So these cam gears can control camshaft timing relative to the crankshaft. And this third camshaft controls the amount of lift on the intake cam. And these engines from the factory, when you hit the throttle and you start adjusting, most of that throttle change is actually happening from a change in intake valve lift. When the intake valve just opens up a little bit, not much air is getting in, just like a closed throttle body, and you're not getting much airflow, and it's like having a closed throttle body. And so the theory is that when you restrict the air intake from the valve, there's less pumping losses than at the throttle body. So factory uses a very complicated tuning setup between what the throttle body does and the intake valve lift.
Okay, interesting.
But in our application, we will install all of these parts, but we then put this third camshaft for maximum valve lift, and we lock it in that position, and we don't use the adjustability.
Right. But now these lifters don't ride on the camshaft though.
On the exhaust, it's very traditional.
Oh, okay.
The lifter goes inside the head, the rocker sits on the valve, and the cam goes on top of the roller, and it just compresses the valve. So the exhaust is very traditional in that sense, traditional for overhead cam, modern engines. The intake, the camshaft, you'll see later, but the camshaft actually runs on this intermediate rocker, and it pivots on that third camshaft, and then the intermediate rocker then contacts the roller on the rocker arm, which then actuates the valve.
Mm-hmm.
This is a special service tool that pushes down on the valves.
Do you have to have that tool? That tool is only for the exhaust cam, not for the intake? Or do you have to do something on the intake as well?
Intake doesn't matter because of the intermediate rocker setup.
Oh, that's right. Okay.
Special service tool. All right, so this is now going to lock it into top dead center.
But that's locking the camshafts in the top dead center. So you're going to have to rotate the crank still though, right?
Yeah. I'm going to put this on slower. All right, so that is the factory flex plate that comes on a Supra. So on the oil pan, there's a hole, and this another special service tool with a nice fluorescent leash goes in the hole, and it lines up with a slot on the flex plate. So currently it will not go all the way in. So I'm going to turn the crankshaft. So what that does, it's now gone into the oil pan, and it goes into the slot, and it's literally locked this thing into top dead center for the crankshaft in the short block. We've locked in the camshafts to top dead center for intake and the exhaust cam with this special service tool. And now we can put the cam gears on, and everything will be lined up. And it's very interesting because the cam gears, there's no clocking of them. You just put them on anywhere. They can go on 360 degrees. And the chain is what aligns it. But there's another special service tool we can get to in a minute. But there's friction that holds all these on. So I'm going to make sure that all with alcohol, I'm going to clean, make sure there's no oil or anything on it. It's that friction material. They have a special feature here that bites into the camshaft so it doesn't want to slip.
So there's zero position, basically. No specific spot for it.
Nope. It's another special service tool for the spline drive. So now these can slip on the cam, right? But so like this could go on any of these ways, right? So we've got another special service tool that goes in where the tensioner is, and it has a spring in it.
All right.
So that goes in where the tensioner goes, and it puts the right amount of tension, whatever that is,
On that shoe. Yep. On the tensioning shoes.
Yep.
Takes up the slack. That way you can tighten up the cam bolts.
So if you watch this, as I tighten this, it gets all the slack out, and it'll put the right tension on everything. Oop, too far. That's it. So now
Nice.
everything's taut, top dead center. Seven, 22, 37, 35 degrees.
Oh.
So now I'm gonna do 35 degrees.
Right.
Done. Yeah, so what we're gonna do now is pop out this.
It'll maintain that shoe position, but it couldn't set it, basically.
Yeah, I'm just gonna pull all
'Cause
this
there's-
stuff out now. Like it is, everything's tight, so,
Right.
and the chain can't fall off,
Right.
so. It's a disaster if you don't have the tools. But if you got the tools, it's actually not that bad. So the way this works is, as the cam spins, the lobe, instead of opening a valve, I mean, it eventually opens the valve, but it actuates this intermediate rocker. The intermediate rocker pivots off of this third camshaft. So it's like an adjustable fulcrum. And then this intermediate rocker actuates the main traditional rocker arm, which pivots on a hydraulic lifter, and that's what opens and actuates the valve. And we're missing a part, like there's a spring that goes in here. So later on we'll have the spring and everything will stay in contact. Right. Yeah. Yes, this special service tool is our intermediate rocker spring installation tool. So what it does is it holds it here, and these two little fingers compress the spring, and then we go ahead and put it in its location, in its seated position. And then you get the trigger, let it go.
Wow.
There's one.
That's a pretty complex tool for putting those in.
Oh, this is thousands of dollars of special tools.
I would think so.
And when nobody had it here, I had to buy it from a friend that lives in Europe from BMW,
Right.
because Toyota didn't even have this stuff available yet. So this is the motor that turns the third camshaft, and that slides in here. That worm gear turns this gear. This is then going to turn this third camshaft. See how it's turning the gear? And basically, turning the camshaft lobe via the motor manually in order for these intermediate rockers to have the most lift, the highest rocker ratio. So this is basically maximum. We're going to bring it all the way up to the stop. So what we've done is we've designed and machined these little stoppers out of steel. And they have a couple of bolts. And then this one that comes in and holds it at maximum. And it'll pinch it in there. The idea is that the stepper motor is actually holding it at that position. The this stop is just sort of not letting it, because there's little detents on this. I'd be afraid that it could move. I don't know. I guess we could pull it off and plug it, but for whatever reason.
It looks to me like this is holding that lobe, right?
Yeah.
Against the...
But I don't know if that pin is strong enough for all of that, but I guess it's machined in. I don't know. We started pulling it apart to sort of design something, but I never had. I never got to that point.
Time better spent somewhere else, maybe.
No, I was just afraid of pulling out the whole motor and then just having that little pin holding it. Probably. Why don't we turn it over and make sure we get a rotation out of this thing? And if you want, you can come around this side and you can see the rocker arm and all that stuff work now. That's kind of weird because it just wipes back and forth. So now the main mechanical part of the engine's assembled. Camshafts all the way down to crankshaft. And now we're going to start basically dressing it, what I would call dressing it. So we're going to do the crank pulley, water outlet, water pump, put the valve cover on it, and some of the sensors and little fittings and stuff. Yeah, so we run an electric water pump because we can't get enough flow out of the factory pump. So we actually open up the water pump and we take all the fins off of it. So this is just like an idler pulley now. And then the alternator goes here and the power steering goes down on the bottom. So this area is where the stock mechanical fuel pump that runs the direct injection lives, but we don't run that. So we have our cool little block-off plate. All right, so now the engine's done in this room, and then Sean's gonna take it, and he and Mario are gonna go drop it into Ryan's Corolla.
All right, Steph, so we have the engines in, obviously built and all assembled, ready to roll, but there's certainly a handful of things left to do here. I guess fill me in on what your next process will be as far as building the car and making everything run.
Yeah, so this engine package is sorted, but only in the GR Supra. Now that we're putting in the Corolla, we can generally use the same engine package as far as that, but the intake manifold and the turbo manifold and all that stuff are different to the engine bay differences. So like we've been working on the intake manifold for this car.
Gotcha. Okay.
So we're gonna use a really similar runner, but the plenum has to be a different shape. And if you look at the throttle body, it's at a bit of an angle. So we've been CAD designing it, and what we'll do is we'll 3D print sample parts out of plastic on the 3D printer,
right,
and make sure that how we envision it in the engine bay, it really is, and then we can do changes as necessary, and get all that stuff sorted, and then we'll have it machined.
Cool. And then I think you were talking earlier too, you're going to do the same thing. The turbo ends up sitting over here. So I like how I saw it set up in another spot where you had the turbo kind of hanging in space, and then you'll basically connect all the way through it. But you were saying you print the exhaust manifold on that as well.
What we'll do is we'll place the turbocharger where we want it. We have a stand for it. And right when we get it where we want it, we'll actually use the roamer arm and get some data points of where those flanges for the turbocharger and then the cylinder head are in space. And then the computer, then we can just import that and start building the manifold in CAD. And then we'll 3D print the runners and stuff out of Inconel.
Oh, wow.
Yeah, we have a great supplier for that. And what that allows us to do is do complicated bends and collectors that would be typically maybe impossible or really difficult to fabricate or could take a long time. So the increased cost in having it printed actually reduces the amount of time to build it, and so it's you can end up with a better final product.
Well, that's cool. I can't wait to see the final product, and we'll touch back with you in a couple weeks.
Awesome.
So after a couple weeks, we got back here to the shop. When we left, of course, it was just a long block, no intake, no exhaust, and then Dom did his magic. So Dom, can you walk me through basically what your guys' process was when we weren't here?
So one of the first things a little different about this setup, the motor is mounted a little bit more vertical than it is in the car. So everything had to be changed. We thought we could use parts from our other car, which has the motor in the factory location, and it's leaned over, probably another 10 degrees or so. So we test fit some of those parts, nothing really fit. So we realized we had to redesign everything. One of the first things we started on was the turbo manifold. So this thing is actually 3D printed out of Inconel, which is excellent for exhaust systems because it can withstand the heat, and it's very strong, so it won't crack. So we had it 3D printed, and then it's done in sections, so it has to be welded together. So I welded everything up. We got the turbo mounted, and then from there we did an intake manifold. So this is all machined out of billet aluminum. It's our own design for this setup. So everything fits the way we want it, and then we did a direct port nitrous setup. So I bent up all the lines for that. This is all stainless steel.
Very nice job, by the way.
Mounted real nice and clean.
Yeah.
And then from there, this is the custom intercooler that we built. So we basically started with a core that you can buy. They didn't really make anything the correct size, so I actually had to use two. So that it's two stacked together. It's welded on the inside, and then I made these custom tanks for it, did all the piping. We did a full custom exhaust for the car, and then pretty much it was ready to go. Brought it to the dyno.
The craftsmanship is absolutely beautiful, Dom.
Yeah.
Again, like you said, you want it to look nice and clean,
Yep.
and be functional, and of course be able to access everything.
Yeah. That's one of the main
things. Did a beautiful
things
job
with building a race car. Everything has to be designed properly, but it has to be easy to work on too, because we're constantly changing stuff. The car could get damaged, we have to replace parts, so it has to be easy to repair and easy to work on.
All right, so I've had a couple of engines at the dyno, and I know how that kind of can be pretty stressful at times. I assume you took this as a full unit as far as a car is concerned.
Yeah.
Wheel dyno. So how did that initial session go at the chassis dyno?
So we have experience with this motor already in two other cars, so we were pretty confident in the base map that we had for the car and how everything is going to go. The only big changes really were this turbo manifold, which is a different design, so we're a little concerned about that. It might require some additional tuning or adjustments. Yeah. So the other car has a hand fabricated stainless steel exhaust manifold, and this one is a 3D printed design. So we built it to be a little bit more efficient, but since it's basically a design that you can't fabricate by hand, we were unsure of how everything is going to work and how the turbo would spool up. So we had to do a few adjustments there with the tuning to make that work properly. But everything else went really well. We didn't fully tune the car to its maximum potential because the first event we're doing, we actually don't need all that power. So we ended up with a little over 900 to the wheels, and I think it was about 900 torque.
Wow. That's nice to have a little more ceiling, huh?
Yeah.
That's pretty awesome.
So we have a couple different turbos that we actually switch depending on what track we run at. And basically what that does is increase the maximum power output of the engine, and also when we go to the smaller turbo, it gives us a better response. So for the smaller tracks, we prefer the smaller turbo because the car is more responsive, and we don't need the extra horsepower. But for the big tracks, we'll put the big turbo, and it makes more power.
Gotcha. All right, well, it looks pretty sitting here. I guess time to hit the track and see what it does, right?
We can't wait.
All right, so we spent the week with Steph putting the motor all together and got it into the car. Obviously, you can see they finished things up quite well. And now it's turned over to you, Brian.
Yeah.
So how does yourself and Ryan feel about the new power plant?
It feels really good now that media day is done and dusted.
Right.
You know, we were a little nervous. Testing didn't go as good as it could, but today went phenomenal. We were able to turn the power up a little bit and give Ryan what he wanted.
Gotcha.
Over last year's engine, the power delivery is so much better.
Right.
We have a wider power range, more RPM.
Right.
Yeah.
So you went from the 4-cylinder
Yeah.
now to this 6-cylinder.
Correct.
Obviously, so you've gained, I assume, a fair amount of horsepower overall, right? And
Yeah,
some
a
torque.
little bit on the weekend, but the torque comes in much earlier.
Ah, okay,
And
yeah.
then it's easy to manage the power number with additional cylinders to take up some of the grunt.
Now, earlier I saw you were going through and doing some tuning and that on
Yeah.
laptop and that. How has it been different than the 4-cylinders?
It's easier to make the power with more cylinders, you know? So we're just fine tuning it here now that we're out off the dyno and in the real world situation.
Right.
It just, those fine tune adjustments are what are needed to push it farther.
All right, cool. So what is your, just out of curiosity, because I don't deal with so many electronics and most of the stuff that I do, what is your tuning piece like that you're looking at? Like, what's the data? What chunks of data are you looking at?
It's a wide
specifically?
spread. You know, you start at lambda, and then you're looking at EGTs, and then making sure you're getting to target boost, or maybe not overshooting target boost.
Right,
And
okay.
nitrous comes into play, and that'll make boost control get a little out of whack. So back to being in the real world, those fine tuning adjustments are what are needed. Yeah.
Okay, cool. All right. So reading the lambda numbers and not pulling out plugs and reading them.
We do that too.
Do you?
Oh yeah.
All
Yeah,
right.
we try to hit it from all angles
good.
because the plug will still tell you something.
Right.
Yeah.
Right.
100%.
Sweet. Well, good deal. Well, it looks great in there, I tell you what.
It turned out really good, and the color combos they did, I think, look fantastic.
Yep.
It needs to look good to go good.
Absolutely.
Yeah.
I agree. I agree.
All right, let the screaming commence. That was sweet. Wow. Thank you. That was cool. You don't know until you know, and then it's like, whoa. But hey, that's how that's done. I can't say enough about it. This was sweet, great experience, and you know what? Get out in the shop, get your work done, because there's some really cool stuff to go out and do with your car. This would be one of them.